Sure. Okay, so hello,
Good
everybody.
afternoon. Okay.
Yes.
Good afternoon and welcome everybody to the European Non-Associative Algebra Seminar. I'm very happy to introduce the speaker of today, Professor Alberto Facchini from the University of Padua. The title of his talk is Heaps and Trusses. Please, Alberto.
Thank you, Salvatore. Today, I would like to tell you something about a topic I began to study only 6 months ago, say, heaps and trusses, but it is a topic that really I find fascinating. Okay, so heaps are an old notion. So they were already considered by Truss and Baer about a century ago. So this is a paper, Theory of Abelian Groups, Basic Property. This is a paper of some years later, an introduction to the concept of heap. Schar is the German word that Truss and Baer used to denote, to call what we now call heaps. And while trusses are a much more recent notion, they begin to appear about 4 years ago, and they were defined and studied by Brzeziński. What I will present you today appears in a paper with Maria José Arroyo Paniagua, with the same title as this talk, and which is available in archive. We posted 2 weeks ago or so. But of course, we then have discovered that some of the things that we did in this paper already appears in a paper published last year, always by Tomasz Brzeziński, Stefano Mereta, and Rybołowicz. Anyway, yes, I must tell you that what I will tell you today about heaps and trusses is due 90% to Tomasz Brzeziński and 10% by Maria José Arroyo and me. Okay, so the reason why heaps have not become so popular in the last 100 years is that they deal with ternary operations, and most of us are not so used to work with ternary operation. So let's see. Suppose that we have a set X with a ternary operation. At the moment, I don't require any identity to be satisfied. So any mapping from x times x times x to x. Of course, these pairs, xp, form a variety of algebras in the sense of universal algebra. I have a set with only one operation, a ternary operation. And therefore, there is a natural notion like for any algebra in universal algebra of morphisms, the mapping that preserves the operation, in this case, the unique operation. So the mapping f from x to x dash that, okay, preserves the ternary operation. Okay. Since it is a variety of algebras, these algebras form a category. We have the objects, these algebras, and morphisms. this category has an initial object, which is the empty set with its unique ternary operation, and a terminal object. The terminal objects are the singletons with their unique ternary operation. In general, in the literature, this algebra with one element is denoted by star with an asterisk. And a ternary operation on a set X is called a Malchev operation if P of, whenever the first two elements are equal, then what I get multiplying, saying these three elements is Y, is the other element, and the same on this, on the other side. So if the last two elements are equal, then what I get is always X. These are Malchev operations. Okay, I've said that usually we don't feel at ease in working with a ternary operation, P, on a set. And therefore, if we don't like our ternary operation, we replace it with a family of binary operations, by, simply fixing this term y is just the term in the middle, okay? So for every y in X, we fix this and we get a binary operation. Therefore, we can replace, if you want, our unique ternary operation with an index family of binary operation, index family indexed in the same set X, okay? It's clear that the data are the same. Of course, from the point of view of universal algebra, they are different things, but in practice, it's this idea is very convenient to visualize our ternary operation, just replacing it with this family of binary operations. For instance, well, correspondingly, we have that for every y, we have a magma. By magma, I mean simply a set with a binary operation. Okay, so we get a family of magmas X by, again, a family indexed in X itself. And, well, in the literature, you will also find that instead of P of XYZ, it is very convenient to denote it is using brackets. And instead of this notation by of XZ for this binary product, just to denote the Y as a with a small letter under the dot. Okay, for instance, what does it mean that the ternary operation P is a Malchev operation? Well, it's very, very easy to see that this simply means that in these index families of binary operations, Y is always a two-sided identity for this magma. You see, X times X, Y, Y is always X. So this means that Y is a right identity for the operation Py. And similarly on the left, therefore, this strange definition of a ternary Malchev operation simply means that the corresponding family of a binary operation on X index in X, all of them have a two-sided identity, which is exactly Y. Okay? In a magma, so also if we don't have any form of associativity, then the two-sided identity, when it exists, is unique. Okay, so Y, in this case, is the unique identity of the magma X by. And what does commutative mean when you have a ternary operation? Well, for a binary operation, commutative means that xz is equal to zx for every x and z. Now that we have replaced our ternary operation with our bunch of binary operations .y, it is natural to say that a ternary operation P is commutative if and only if all these operations .y are commutative. Okay, so by definition, we say that a ternary operation P on a set X is commutative if P of x, y, z is equal to P of z, y, x for every x, y, z in X. Of course, this motivation, the motivation of how I have introduced this notion of commutativity might seem a little naive, but we will see in half an hour that for heaps, like for several other algebraic structure, it's possible to define a notion of commutator, of congruencies, and that a heap is commutative, is abelian, say, if and only if all its congruencies commute. So we will give a deeper motivation for this definition of commutativity of a ternary operation. And well, what I said, for groups, given any group G, it is possible to define the commutator of any pair of normal subgroups M and N of G. This is again a normal subgroup of G contained both in M and in N, and G is commutative, is abelian, if and only if the commutator is exactly 1, okay, for all its normal subgroups M and N. So we will see that also for heaps we'll have a similar motivation. And what does associative mean when we have a ternary operation? Well, for a binary operation, associative means exactly that this formula holds. Again, we have replaced the ternary operation P with a bunch of binary operation .y, and therefore it's natural to say that the ternary operation P is associative if and only if we have this associativity whenever, for every y and w in X. Okay, so associative, a ternary operation is associative if this formula holds. I'm just trying to introduce in a very elementary way these the behavior of a ternary operation. So what does Malchev means? Essentially that there are two-sided identities. What commutative means for a ternary operation, what associative means for a ternary operation. Okay, so in particular, when y here is equal to w, we get that if our ternary operation P on a set X is associative, then all the binary operation by are associative. Okay, so that this means that all these magmas are in fact all these operations are associative, so they are all semigroups. Okay, and now we can define what a heap is. A heap is a set X with an operation that is both associative and Malchev. Okay, so for what we have seen, all those operations by have a two-sided identity y, Malchev, and we have that form of associativity. Okay, so also for heaps, we have our definition of morphism between two heaps, just that the operation is preserved like before. And we get a category denoted as a heap, and in heap, the empty set, the empty heap is the initial object, and the terminal objects are the heaps with one element. Okay. Except for the empty heap, for which there is not so much to say, then we have just said that these magmas, since we have associativity and a two-sided identity, all of these are monoids. But in fact, they are not only monoids, but they are all groups, and they are all pairwise isomorphic. It's easy to see that they are groups because the inverse of any element y in X, here we are in Bx, is exactly this. It's just an elementary, it's easy to verify it. And they are all isomorphic groups because there are group isomorphisms from XBX to XBY. These group isomorphisms are this mapping tau. They are called tau because, in fact, they are a sort of translation. So a translation from X to Y of this group onto this group, and it is defined just, the translation is just the ternary operation Z, X, Y. Okay? Very well. And then we continue with the elementary notions of universal algebra. So we have our algebraic structures satisfying heaps, okay? Satisfying our axioms to the ternary operation is Malchev and associative. I have morphisms in the sense of universal algebras, and I have substructures, subalgebras. A subset S of a heap is a subheap if it is closed for the unique operation. So if XYZ is in S for every XYZ in S. Examples. Well, this is an example that I have learned from George Gianelizze, who had learned it from Thomas Brzeziński. Consider our space of physics. So we live in R3, okay? I'm not talking of modern physics like a quantum of relativity or so on. When we work with our Newtonian physics, we are in R3, okay? Our three-dimensional Euclidean geometrical real space. This space, the space in which we live, doesn't have a natural group structure. I've said we work in R3, R to the 3, but in fact there is not a natural structure of vector space of the group because the sum of 2 points in our geometrical space E3 doesn't have a natural meaning because essentially there is not a natural origin in our space. We can fix it wherever we want. But to have an abelian group structure, we must fix an origin, a point, and then we can define an addition using the parallelogram rule, and in this way we get an abelian group. In fact, we get, as we know, a three-dimensional vector space over the field of real numbers. But it is necessary to fix an origin, which is not a natural. In fact, we know that every point of the space can be chosen to be an origin. Okay, so E3 does not have a natural group structure, but it does have a natural heap structure. If we take any 3 points in the space, we can always say A, B, C. We can always construct with the 4th point with the parallelogram rule, okay, getting the vertex of a parallelogram, and what we get is a heap, okay? So I've given you this example because really our three-dimensional space in which we live doesn't have a natural structure of abelian group, but does have a natural structure of a heap. The ternary operation is, given any 3 points A, B, C, construct with the parallelogram rule the 4th vertex of the parallelogram. Okay, and then if we want to, we can fix any line in our space, and we get a subheap of the previous example, or any plane in our space, getting a subheap. Okay, so this was just to show you the naturality of the notion of a heap. Our three-dimensional Euclidean space is a heap, has a natural heap structure. A second example is given any group G, multiplicative group G, say, we can define a ternary operation P on G, saying that the product of the 3 elements is X, Y minus 1, Z. This is a ternary operation on a group G, and one gets a heap. And much more can be proved that if I take any non-empty heap, it is always isomorphic. So we are in a category, so being isomorphic has a meaning. Every non-empty heap is of this form, is isomorphic to a group G with this operation. Okay? In fact, this is a functor from the category of groups into the category of heaps. If I have a group G dot, I associate to it the heap GP, where P is this operation. And I don't change the morphisms, are always the same mapping, and I get a mapping. Okay, so thanks to this remark, there is not a great difference between heaps and groups. All heaps are of this form, okay, correspond to some group. The only difference is really that we don't have a zero, we don't have an origin. And so I have this natural functor from groups to heaps, but the two categories are not equivalent, okay? For instance, the category of heaps doesn't have a null object, okay? We have an initial object, which is non-isomorphic to a terminal object. But also if we say, well, we could have eliminated the empty set, empty heap from our category. Anyway, the category are not equivalent also. Okay, so now that we have seen that there is this strong relation between heaps and groups, let's begin to describe that we are in universal algebra, the congruencies. Of course, congruencies, well, in groups, we know that they are related, they are in one-to-one correspondence with normal subgroups, and something very similar occurs for heaps. So if I take a subheap S, non-empty subheap of a heap X, the following conditions are equivalent. That there is an element such that for every X in X and every S in S, there is a T such that this equality is satisfied, or this property doesn't hold only for one element E, but for every element E in S, or this last condition. Let me explain you a little what these conditions means. Here, if you think of the corresponding group X with the multiplication based, the binary operation based in E, so this means that for every X and every element S of the subheap, XS is equal to TX from some X. This is exactly the standard definition of, well, the left coset XS in the group is contained in the right coset. And this is sufficient to define, it's one of the possible definitions of what a normal subgroup is. And this is true, if it is true for one element of S, it's easy to see that it is true for every element E, so whenever the base point is fixed. And this condition is exactly the condition X, S, X minus 1 belongs to S for every X in X, S in S. So they are really the standard equivalent definition of what a normal subgroup is for a group, but just using now the ternary operation on the heap. And a subheap of a heap is said to be normal if it is non-empty and satisfies these equivalent conditions. And if we want another equivalent description of normal subheaps of a heap X is that there exists an E in S such that S is a normal subgroup of this group, or that the same condition holds, well, S is non-empty and it is a normal subgroup of XB, the same condition holds for every E in S. Okay, so normal subheaps correspond really to normal subgroups of the corresponding groups. But what is more, some care here. We have chosen our terminology in such a way that the empty set is a heap, okay? And in fact, it is a subheap of every heap. It is contained in every heap. While we have defined normal subheaps to be non-empty by definition. So as a consequence, we have that subheaps of a heap form a complete lattice, because every intersection of subheaps is a subheap. In fact, this is a property again of universal algebra. Any intersection of subalgebras is a subalgebra. And therefore, this is true also for heaps. Or, again, another property that is general in universal algebra, an intersection of congruencies in universal algebras is a congruence. And therefore, again, congruencies on a heap form a complete lattice, because every intersection of congruencies is a congruence. But normal heaps of a heap don't form a lattice in general. They're just a set partially ordered by inclusion, because we can have that the intersection of two normal subgroups can be empty, and therefore it is not a normal subgroup. According to our definitions, normal subheaps are non-empty. We will now see very soon that there is a sort of correspondence. I'm not saying one-to-one correspondence. Now we will see this in detail. Anyway, there is a relation between normal subheaps of a heap and congruencies on a heap. Again, the notion of congruence is a universal algebra. And so a congruence on a heap is an equivalence relation compatible with the operations, in this case, the unique operation on the heap. So whenever x is equivalent to x dash, y to y dash, and z to z dash, then when I compose them with my ternary operation, I get equivalent elements. Okay, for instance, it is possible, this is just an elementary example, in a commutative heap, all non-empty subheaps are normal. This is the analog of, in a commutative grouping, in an abelian group, all subgroups are normal. Okay, now, for a good algebraic structure like a group G or a ring R, we have a one-to-one correspondence between congruencies and equivalence classes modulo the congruence of 0. Okay, this is the correspondence that gives us normal subgroups of G. In the case of a group, it is the equivalence class of the identity of the group with respect to the corresponding congruences, or two-sided ideas of R. Now, in the case of heaps, we don't have a 0. Okay? In fact, we have just shown that every element can be chosen to be a 0. Every element in the space can be chosen to be the origin. Okay? So we don't have equivalence classes of 0, but we can have equivalence classes of any element. And therefore, now this is a much larger class than in the case, than in the case of groups. And therefore, in fact, we will show now, we'll say, see that we don't have this one-to-one correspondence anymore, but only an onto mapping in this direction. Okay, let's be more precise. So there is, for heaps, an onto mapping from normal subheaps, from the set of all normal subheaps of a heap H, and the set of all congruencies. Okay, let's give an example. I've said, okay, let's consider the heap Z of integers, okay, with their operation A minus B plus C. Okay, we have seen that this is a heap. It's possible to see that what is what are its subheaps? Well, they are exactly its cosets, okay, plus the empty set, the empty subheap. This is the complete lattice of its subheap. The normal subheap, well, in this case, it's an abelian group, it's a commutative, so its normal subheap is just all non-empty subheaps, okay? As we know, this is not a lattice, it's only partially ordered by set inclusion, because we can have A plus BC intersected C plus DZ equal to empty set, and the empty set does not belong here. And the congruences are the usual congruences modulo n. Okay, so the complete lattice of congruences is the set of all congruences modulo n, where n is a natural number, a negative integer, and therefore it is isomorphic to the lattice n divides, that has 0 as its greatest element and 1 as its least element. Okay, so there is this onto mapping from normal subheaps to congruences. If I have any normal subheap, the corresponding congruence is defined in this way: if x, y, s belongs to S for every S in S. Again, what does this mean? It means x, y minus 1, S is in S. Well, this is equivalent to x, y minus 1 is in S, and this is exactly the definition of the congruence corresponding to, in a group, corresponding to the a normal subgroup S. Okay, so there is this constant parallelism. Okay, in our example, for example, in our example of the heap Z, this onto mapping, it sends any normal subheap A plus BC to the congruence modulo absolute value of B, okay? And again, we see that this is an onto mapping, but it is not a bijection, because, well, for several reasons, anyway, this is just an onto mapping. Okay. If we fix an element, E in Z, then there is a one-to-one correspondence. This onto mapping becomes a one-to-one correspondence between normal subheaps that contain a E and congruences. This is a general fact. So if I have a heap and I fix an element, then there is a lattice isomorphism between the lattice of all congruences of the heap X and the lattice of all normal subheaps of X that contain E. Okay? So if I reduce the number of, I don't take any subheap, but only those that contains a fixed element E, then I get a bijection. Okay, and the bijection associates with any congruence the equivalence class of the element E. Now that we have fixed an origin, a privileged element, then we can take the equivalence class of that element. Conversely, like for groups, given any normal subheap S of X, that contains E, the corresponding congruence on X is defined with the formula that I said before. Forgive me, but I prefer to jump a little. I had prepared several other things. I'll make this slides available to everybody. But until now, I have talked about heaps. And I would like to say something also about trusses. So let's say with trusses, let me jump to the case of trusses. Okay, here we are. Here, well, of course, in all what I'm telling you now is in that papers on archive. So if you are interested, if you like this topic, as I do, you find everything in detail in that paper. Okay, let's take about trusses now. We will consider here left near trusses, which is the analog of left near rings. But now, what is a left near truss? It is, again, an algebra in the sense of a universal algebra with a ternary operation and a binary operation. Okay. With respect to the ternary operation, this is a heap. With respect to the binary operation dot, it is a semigroup. Okay, so it is associative, this operation. And left distributivity holds, like for left near rings. So X times a composite of 3 elements is the composite of the 3 elements multiplied on the left by X. Similar, of course, it is possible to define right near trusses exactly in the same way, where instead of this left distributivity, we use right distributivity, which is this formula. Okay, clearly the category of the left near trusses is isomorphic to the category of right near trusses. It suffices to associate with any left near truss the opposite right near truss, which has the same heap structure, and the operation is the opposite operation. Some examples. You know that when we have a group and we take all mappings from a group G to the same group G, we get a near ring. The same thing is for heaps. So if I take a heap and I consider M of X the set of all mappings, so just any mapping from X to X, then we can define a ternary operation on M of X pointwise, saying that the product of the 3 elements of 3 functions computed in X is the value of the 3 functions computed in X for all X in X. So the pointwise operation. And one gets a heap in this way. It is just the direct product of the cardinality of a set of cardinality of X copies of this heap. And as multiplication, we take composition of mappings as our binary operation. And in this way, one gets that every, like in the case of groups, all mapped G of a group G, all mappings from a group G to a group G form in a natural way a left near ring. In exactly the same way, we find a right near truss. Also, if we begin from any left near ring, we can define, we just modify this operation of addition, of multiplication. It is a non-commutative in general, but we modify it as we do for groups using this formula. Recall that I'm using addition, but I'm not, this doesn't mean that the operation is commutative, okay? And what I get is always a left near truss. So from any left near ring, it is possible to construct a left near truss. For those of you who know what a left skew brace is, it is possible to define in the same way. A left skew brace is a set with two binary operations, and with respect to both, B is a group, okay? Plus another condition. Okay, we can define a ternary operation using the first operation, okay? So this is the inverse with respect to the group operation star, okay? And we get a left near truss, okay? So several possible constructions of left near trusses. There are two messages in the chat. Let me see if there is any relation between heaps and n-Lie algebras. Oh, I'm sorry, I don't know what n-Lie means, so I'm not able to answer you. Of course, you can, when you have an additive structure, you can always replace the group structure with this operation. But I'm not able to answer you in detail because I don't know what n-Lie algebras are, so forgive me. Okay, let's continue. The right near truss of example 1, so all mappings from X to X, is particularly interesting because every right near truss is isomorphic to a sub-near truss of M of X, okay, for some heap X. Okay, so up to isomorphism, these trusses, right near trusses, contains all possible right near truss up to isomorphism. In fact, in some special cases, if I have a left near truss and I take and our element Y has some special property. So if I have any left near truss and my element Y is a right zero, okay, for this semigroup, so this means that X times Y is Y for every X in X, then what I get taking X, the operation BY, okay, so the group operation constructed from this, fixing the element Y as an origin, and the multiplication, I always get a left near ring. So it is necessarily sufficient that the element Y is a right zero in this semigroup. And if this is a group with respect to the second operation, and Y is an identity, it is the identity of this group, then what I get is always a left skew brace. Okay, so there is really, this is why Brzeziński introduced these things that he introduced trusses because of their relations with rings and braces. now some terminology, some further terminology. A left truss is a left near truss in which this heap is abelian, is commutative, similarly for right truss, and the trusses that were originally defined by Brzeziński 3-4 years ago are exactly the left trusses that are also right trusses. Okay, so what is a truss? Is a set with a ternary operation and a binary operation, where this is an abelian heap. Okay, so associative, commutative, and Malchev operation. This is associative, it is a semigroup, and both distributivity laws hold. Okay, I go rather quickly because I have only 10 minutes to conclude. The main example of a ring with identity is given any abelian group, G, you take its endomorphism ring. Okay, exactly the same thing can be done for heaps. If we take any abelian heap and we construct it, and we consider its endomorphisms, what we get is a truss, the endomorphism truss of our abelian group. Okay, so the main example of truss is take any abelian group heap X, you take the set of all heap endomorphisms of the heap, the operation P pointwise that we have already met in M of X, and composition, and we get an example of truss, the endomorphism truss of any heap. Okay, again, I don't have the time, so I skip very quickly on describing what the congruences are. Again, they correspond to particular ideals, which are defined in a way very similar to how the property of ideals in near rings. And again, we have this onto correspondence between ideals and congruencies of the left near truss. Okay, a relation with the distributivity. Forgive me if I'm not very much detailed now. Okay, it's possible to discuss Hack commutator and Smith commutator for near trusses, what semi-direct products are for heaps and left trusses, what derivations in a truss are. Okay, but I want to conclude with a wonderful result by Brzeziński and Simeon Breas. Well, there is a very classical result due to Baer and Kaplansky of half a century ago, 70 years ago. They proved that two torsion abelian groups are isomorphic if and only if their endomorphism rings are isomorphic. Okay, and moreover, if I have any ring isomorphism between the endomorphism ring of G and the endomorphism H, then there is a unique group of isomorphism between the two torsion abelian groups, such that phi is exactly, let's say, the conjugation by phi, small phi. Okay, it is still unknown. You see, this is true for all torsion abelian groups. It is not known if this result is true for any two 1 billion groups, not only for torsion case. This is a problem that is still open. Okay. Simeon Breas and Tomasz Brzeziński last year published the fact that it is always true, that conjecture, if we consider endomorphism trusses. So 2 abelian groups, G and H, are isomorphic if and only if their endomorphism trusses are isomorphic. And any truss isomorphism between them is induced by a unique heap isomorphism, small phi, between the two heaps corresponding to the abelian groups G and H, okay, such that big phi is just, let's say, the conjugation of is just the truss isomorphism induced by the heap isomorphism, small phi. Okay, this is all what I wanted to say today. It has been much less than what I would have liked to say, but you will well, have a look in archive and you will see several other results, like what are derivations, semi-direct products, and so on for heaps and trusses. Let me just
Thanks,
see.
Alberto, for your interesting talk. Are there any questions, comments, or remarks?
I've tried to be very animated. Please.
Yeah, there is a question on the chat. What would be a reciprocal for the first lemma?
Don't see it. Ah, thank you for the answer. What would be a reciprocal for the first lemma? What is the first lemma? Fatma, what do you mean? Put your microphone on. What do you mean? On page 6.
Page 6.
Page 6. Okay, so this is page 1, 2, 3, 4. This is, well, it is already an if and only if. So it is a Malchev operation if and only if the corresponding index family of binary operation, all of them have an identity. So I don't know what you mean by converse. This is already if and only if, so I don't see what you mean by having an inverse for this lemma. Okay. Thank you all for your attention. Oh, brace or skew left brace? Wait a moment. Okay, so well, yes, braces are related to. Let's begin with pre-Lie algebras, but so the direction is not immediate. Agata Smuktanovich does it essentially for finite groups, so she doesn't have a problems of convergence. So
with some assumption on the potency, of course.
yes, probably
Yeah.
the natural. Well, I tell you that my answer is I don't know. Anyway, it shouldn't be an algebraic structure related to a heap, but an algebraic structure related to trusses. Well, I know that there are people working in cohomology theory and so on for groups, and also, for instance, about structure that you obtain from Hopf algebras instead of having, well, replacing the group structure with the heap structure with the ternary operations. So I know now, really, if you look at just type, well, and anyway, it's really, everything is really very new. So yes, if you are interested, there is really a lot of things to do to develop a nice cohomology theory and so on, or to apply it to other algebraic structure, like structures like Hopf algebras or Lie algebras, for instance, also. Not only Lie algebras, but Lie algebras. I'm sure that you can develop, find connections. Of course, those that are critics with respect to heaps are those that say, well, but look at that heaps and groups are almost the same things. So why is it necessary to develop a theory for heap when it is always everything so similar to what have been done for group? And I understand the points. Anyway, I've found really fascinating working with this ternary operations. Really, now I'm really fascinated of non-associative structures, non-distributive operations. Now with ternary operations, I really like this dance of algebraic operations that have these strange behaviors. Anyway, yes, there is a lot that still has to be found, to be discovered.
Okay, further questions? Yes, there is another question from the chat.
Generalizations to n-ary operations. Well, I haven't seen them in the literature, to tell the truth, until now. Anyway,
Okay.
It's a good question. Another possible direction.
Thank you. Other questions, comments, or remarks? Okay, if not, let's thank Alberto again.
Thank you all.
And we will resume on next Monday, as usual, at the usual time. See you. Bye-bye, everybody.
Bye-bye. Thank you.
Patience.